or refer back to it later. Welcome, my name is Ryan Hoger with Temperature Equipment Corporation. This week's webinar is on IECC 2015. I just noticed the typo on my slide. It is not the 2105 code. Most of us will be dead by then. So the 2015 code. And specifically with a focus on the challenges related to helping rooftop units comply. Some of you guys were on the various webinars we had the past couple weeks. The information we're going to talk about today, for the most part, was covered in some of those webinars. We're just going to go into a little bit more detail on the rooftop specific stuff and really focus in on that. A lot of folks didn't want to come to the first webinar because they didn't care about residential, and they didn't care about chillers, and they didn't care about boilers and all that stuff. They just care about rooftops. So we decided to do this this third one just to kind of help those folks out that are really focused in on rooftops. So a couple of the things will be recap here, and then we'll jump into the rooftop discussion. For you guys that need PDH hours, you would have had to indicate that when you registered by clicking on the box saying you're in Illinois or Wisconsin PE and you need the PDH certificate. And then there'll be 5 quiz questions that pop up during the course of this broadcast. You will need to answer 3 of the 5 correctly. They are not hard, but you do kind of have to pay attention in order to get them correct. And that's the way we prove to the state that you did participate. All right, here we go. So as you know, the reinvigorated focus around the 2015 code is because in Wisconsin a month ago, that code went live for commercial projects. So that's why it's kind of been interesting again, and people keep asking us to do the webinars again, even though we did them a couple years ago. And it's also a good review for you guys in Illinois as well. So this applies to both Wisconsin and Illinois, as well as any other state that's on the 2015. Wisconsin eventually on this map will turn dark blue, just like Illinois. And then you can see the other states in the very dark blue are also on the 2015. So we're up to 13 states that are on the 2015 IECC or the ASHRAE 2013, which are functionally equivalent. You've seen this chart numerous times, and you've seen that over the years, these savings targets for the code get more and more aggressive. The difference between the 2012 and the 2015 is about 8 to 9% savings. For you guys in Wisconsin that are updating from the 2009 to the 2015, the jump's about 30% for you guys. The vast majority of the changes from 2012 to 15 on the commercial side are rooftop related. So when does the IECC 2015 comply? First of all, if you're in a state or jurisdiction that's following it, obviously. But then in the document itself, there appears to be some things that are accepted. When we start reading the language, those exceptions don't really apply to us on the HVAC side. For example, you'll hear that, oh, you don't have to necessarily do everything in the book if it's just an addition. However, when you go read the section related to additions, it says you must comply with section C403, which is the entire mechanical section. Same thing with alterations. It'll say alterations, follow C403. Well, that's pretty much the entire mechanical section. And it even points out on there, in relation to economizers, if you were changing out a rooftop, you might think, oh, the economizer is not part of that. They specifically spell out the economizers need to be updated and brought up to code as well. Repairs as well. If you're going to repair something, the new repair needs to comply with the current code. You don't have to bring the whole system up to code, just the thing that you're repairing. Right? So the essential rule of thumb is, if you touch it, you need to make it comply with code. If you leave it alone, it can stay the old code for as long as you wish. I will mention as well that the real true exception is historic buildings. So if you look down the bottom right there, I didn't blow it up, I should have. C501.6. Historic buildings often get an out for certain things if it's going to affect the historical nature of the building, right? So like a rooftop in view of the line of sight of the street may have some exceptions and things like that. So historic buildings are your one out for not complying with the code. There are 3 ways to comply with the commercial provisions of the code. You're probably aware of this already, but just for a quick recap. One way is take your code book and throw it out and not use it at all. Just follow ASHRAE 90.1 2013 instead. You could do that. Another way would be option number 3. And that would be do all the things that are listed as mandatory in the book, but skip all the things that say prescriptive. However, you need to do an energy model of the project you want to build, the way you want to build it, and energy model the same project as if you did do all the mandatory plus prescriptive. And then you got to beat that by 85%, or beat it by 15% rather. You could do that and comply. That way, if you say, well, I want to do a VRF system and it's not really conducive to economizers, what am I supposed to do? Well, save extra on the VRF itself, extra energy, and trade that off against the economizers, that kind of thing. In Wisconsin, you don't have to beat it by 15%. You just got to match it. So that's a little bit of a difference there. For today's purposes, we're going to stick on item number 2, which is do everything in the book that says mandatory and do everything in the book that says prescriptive, and don't worry about any other codes like 90.1, and don't worry about energy modeling and software and any of that. Just do everything it says in the book. That's what we're going to stick on for today, because that's the easiest thing to kind of have a conversation like this. All right, so the first quiz question. I said these won't be hard, but if you need PDHs, you do need to answer them. And each person would need to answer them. So if there's 2 of you sitting there at one computer, only one of you is going to be getting a certificate for compliance. That's been a confusion point in the past. I don't know why it's written in the instructions, but I know people don't always see every little note. All right, first question. It should be super easy. What is the current energy code in Wisconsin and in Illinois? Option A, 90.1, 2015. B, 90.1, 2016. C, IECC 2015. D, 2016. E, 2018. Which one are you required to comply with in Illinois and Wisconsin? Roberto, I see that you typed your answer into the question chat box. Instead of doing that, because that won't get registered anywhere, do it on the on-screen quiz poll. That way you get credit for it if you need those hours. I see a couple of you guys have typed in that the audio is doing something similar to it did last week with cutting in and out. I can't really solve that any further right now. Like I said, I got an external microphone I just ordered the other day. It should be here. So all my future webinars will hopefully be cleaner. But I do apologize on these ones. All right, I'm going to close the quiz question in 5, 4, 3, 2, 1. All right, 93% of you got the correct answer, which is IECC 2015. All right, so back to our slides. All right, first thing in regards to rooftops, the sizing of the rooftop and the efficiency of the rooftop. Those are going to both come into play from a code mandatory standpoint. So on the sizing, just like other systems, packaged rooftop units are required to have a load calculation done per the energy code. The load calculation needs to be in accordance with the ASHRAE standard for load calcs. So that's pretty self-explanatory. At this point, if people do load calc, we'd be better off, let alone doing it correctly. You are required to use certain indoor design temps. Specifically, the heating must be 72 or less as your design temp, and the cooling must be 75 or more for your design temp. You are not allowed to design a cooling system for 72 or 73 or 74 degrees. 75 is the coldest you're allowed to design it for in the interior space. I mention that because those two things are often things that get tweaked, if you will, in order to help somebody oversize. A lot of folks try to oversize for some unknown reason, I don't know, which, as you know, oversizing just really hurts your dehumidification pretty bad. But they try to do it, and they do it by tweaking some of these inputs. So the code has figured that out, and they've started dictating the inputs to you. In regards to sizing of the equipment, you're required to size it per your load calc. That should seem obvious, but we used to always say that. So in order to clarify that, someone would do a load calc and size it however they want it anyway. But you can no longer do that. You do the load calc correctly, size your equipment to match the load calc. You're not allowed to install equipment that is larger than your load calc. There is an exception to that, specifically geared towards packaged rooftop units. That is, you're allowed to go up on the heating or cooling size, not both, one or the other, in order to get the capacity of the other satisfied. So if you need a 10-ton unit with, 200,000 BTUs of heat, and your choices are a 10-ton with 180 or a 10-ton with 220 on the heat, you could pick the 220, even though it's more than your heating load. Right? So you're allowed to upsize one or the other on a packaged, bundled heating cooling system. Because they realize that not every rooftop has an infinite number of size choices. Then the question comes up, well, what outdoor air temperatures do you design for? Right? The code's dictating 72 and 75 indoor, but what does it say about outdoor? Right? It's directing you back to the ASHRAE documents. And if you look at the ASHRAE Handbook of Fundamentals, and a lot of you guys are in Wisconsin and a lot of you guys are in Chicago, so I'm going to look at those two things. If you look at Chicago, say O'Hare, which is kind of considered our area default, if you will. For the heating side, you can design for -1, 1.5, technically, right? And that's if you're going with a 99.6% scenario. And on the cooling side, you could design for a 91.4 would be your most aggressive setting. You're probably better off doing 88.7, which is the 1% number. But if you are a little paranoid, you could go as high as 91. What you cannot do is design for the traditional -10 and 95 like everybody in Chicago did for decades. That would not be allowed. So -1 and 91 would be your typical outdoor air design points for Chicago. And then if you're in the suburbs, there's differences to that on the chart here. Wisconsin, if you were at Milwaukee, it would be -1 and let's say 89.6. However, Wisconsin's state code has an amendment that says exactly the outdoor temps that you need to use per the state code. So the ASHRAE handbook is then superseded by this amendment for Wisconsin. So for Milwaukee, it would be -10 for the heating side, and it would still be 89 on the cooling side. So they've chosen to lower the heating design point in Wisconsin. You can see most of these are -10, -15, -20 type numbers, unless you get really far up north. That's an exception, or I say exception. That's a difference in Wisconsin versus other states that follow this code. If you look at the load profiles for both Chicago and I'll show you Wisconsin as well, Milwaukee, I'll show you. And if you need it for another city, let me know. I can give you the same kind of chart for most major weather cities. But I got Chicago, Milwaukee in the slide deck here. If you look at the EER, which is the full load efficiency of any piece of HVAC equipment, that's always occurring at 95 degrees outdoor temperature. That's what it's tested at in the little lab chambers, right? So EER would be there, but that doesn't really affect me in Chicago. Like how many days is it 95? Statistically, not very many. So I'm more concerned about what's going on when it's 75, 80, 85 degrees outside. So for that kind of scenario, we have what's called IEER, Integrated Energy Efficiency Rate. More run hours at that number. So EER is, I don't want to say not important at all, but it's very little importance relative to IEER because of the amount of runtime it will affect. Milwaukee, similar scenario, right? There's hardly any statistical days at 95, but there's a boatload of hours at 65, 70, 75, 80 degrees for cooling, right? Same kind of scenario. IER, the way that works is you do the full, when I say you, I'm talking about the manufacturer's testing group. They do the test for EER at the full 95-degree outdoor condition, 100% loaded, right? They do that. And they test it again at 75. They test it again at 50% capacity, and then at 25% capacity. And then up in the top, there's a formula up there telling you how they're going to weight those, right? So 2% of the weighting applies to the full load. 62% of the weighting applies to the three-quarter loaded. 24% of the weighting applies to the half-loaded scenario, and 12% of the weighting applies to the quarter-loaded scenario, right? And then it looks at that. So it's really 4 test points, but it's kind of weighted average into a single number to make it a little bit easier to digest, if you will, and easier to compare one piece of equipment next to the other. So when I look at packaged rooftop units specifically, what efficiencies do I need to get to? Well, if I'm below 65,000 BTUs, right, then I'm getting rated by the residential AHRI standard. Even though it's a commercial unit, it's going to go in a commercial application. We call it a rooftop. It's probably going to go on the roof. It still falls into the residential rating standard when it's 5 tons and less. In that scenario, it's not a split system. It's packaged because it's a rooftop unit. I need to have 14 SEER. It needs to be my efficiency rating. All right. If I go to a larger unit, between 65 and 135,000, so like a 10-ton unit, for example, I need to be 11 EER and 12.6 EER. There are, in fact, 2 columns listed here. This column is obsolete. It's only based on if this was 2015 and earlier. Once January 1st, 2016 happened, then we went to this column. So that 10-ton type unit, 11 EER, and 12.6 IER. And then as the sizes get larger and larger, the capacity or the efficiency ratings get a little bit easier and easier to hit. When you're looking at these charts, you'll see for each category, in this case, air conditioners, air cooled, then I have a size to choose from, right? And then after that, in this particular case, I can either have cooling only or electric heat-based cooling or any other type of heating system, which would be natural gas, propane, hydronic coil, heat pump, anything like that. Then I would have to follow this row instead of that row, right? That's kind of how that works. All right, so those are the efficiencies I have to hit. So you guys have seen this software tool before in numerous other webinars I've done or classes. It's just a little quickie 5-minute tool. This is a Chicago example. We can do them from Milwaukee as well, or any other city for that matter. This one has a basic entry-level carrier unit, like the lowest efficiency carrier unit that you can find on a shelf somewhere, right? It has that unit. And then comparing that to a unit that meets the EER and IEER requirements of the 2015 IECC. So in this case, it's 48TC versus 48HC. Everything else is identical. The tonnage, the heating capacity, the heating efficiencies, economizers, everything's identical except for the IEER and the EER, right? And then if you would hit calculate, this software tool would spit out an answer to you telling you how much more that unit saved. In this case, 1%. It's not a massive savings. And in fact, anywhere in the northern half of the country, it's not going to be a massive savings. Actually, even in the southern half, it's not massive, right? But 1%, $27 a year is not enough for me to get remotely excited about. I got to do it. I got to do it to comply with code, but I'm not going to be bragging to anybody about how great I did by putting in this bare legal minimum efficiency unit. Right? You can certainly get units that are more efficient than that. All right, quiz question number 2. Which of the following does not have to comply with IECC? Which of the following does not have to comply? I stress not because everybody complains to me later. I didn't realize you meant not. I mean not. Right? All right, so choices. A, new construction. B, alteration. C, addition. D, historic buildings. E, repairs. 4 of those 5 always have to comply. 1 of those does not always have to comply. Which one is it? Let's see if anybody typed any questions in. I don't have any new questions at the moment. If you have questions you want me to answer, type them in. I'll do my best to answer them. But you guys are voting on this answer pretty quick. Most of you are getting it right, but a couple of you are struggling, and you're struggling in the same incorrect way. I'm going to close the quiz question in 5, 4, 3, 2, 1. The correct answer is D, historic buildings. 81% of you got that correct. Everybody who didn't get it correct said repairs. That would not be true. If you make a repair to an HVAC system, the item you're repairing needs to comply with code, but just that item. So if you were to change out, I don't know, a motor on some piece of equipment, the new motor you put in would have to comply with the code, but the entire unit itself would not. Just the thing that you're repairing and replacing, right? But fortunately, a couple guys got stuck on that a little bit. All right, go back into our slides. All right, let's talk about economizers. That is by far the largest change on the 2015 code is all the changes related to economizers. So we're going to cover everything on economizers here because it's obviously a very integral part of a packaged rooftop unit. Most of you guys know what economizers are, right? It's our way of getting cooling into a building without running compressors. It's the equivalent of opening all the windows up on a nice cool day when you want the building to cool down, but you don't have any windows to open. So you open the window out there in the packaged rooftop unit and suck the cool air in that way and send it through your duct. As you know, there are 3 main ways we have historically controlled economizers in the Midwest. The dry bulb economizer is the most common by far. Historically, we've set those up for 55 degrees outdoor air temperature. Right? Below 55 degrees, it's an economizer day. If it's above 55 degrees, it's a compression day. That's typically how we set them up. That wasn't the best way, but that's what we had been doing for many, many years. And some of us, well, at least me personally, 20 years ago, I started bumping that number higher. 60, 62, that kind of thing. You could do an enthalpy economizer. Enthalpy, as you know, is a measurement of both sensible and latent energy. So it's kind of like looking at the outdoor air temperature and humidity both. And if both of them are low, go ahead and use it, right? I don't mind taking 67-degree air to help me cool the building as long as that air is not super moist because it's raining outside. And then the best way would be differential enthalpy. You would look at the enthalpy of the outside airstream and the enthalpy of the return airstream and compare them. If the outside air is lower than the return, take it. So if my return is 85 degrees and humid, but my outside air is only 80 and humid, it's obviously better. Take the outside air, right? Even though it's not awesome, it's still better than the return air. All right, so those are the three main ways we have controlled them historically. Look at those on the psychrometric chart, and I'm assuming most of you guys have seen psychrometric charts before. Just a quickie refresher. These numbers on the bottom axis are dry bulb temperatures. On this axis over here on the right-hand side, that is absolute humidity, actual real moisture molecules, or grains of moisture, if you will, right? And these curved lines right here, let me get my little 60% relative humidity, 40% relative humidity. They're curved, right? Humidity is relative to both temperature and moisture content, so they are curved lines. And then obviously this line right here is 100% humidity, and there's no chart on the left over here because we never have more than 100% humidity, at least for HVAC systems. So if I had set the economizer for 55-degree outdoor air changeover, it'd be right here on this yellow line. Everything to the left of it, if it was colder than that outside and I wanted cooling, we'd open the economizer. If it was to the right of that and we wanted cooling, we would turn on the compressor. Right? And there'd be no middle ground, if you will, on a traditional system like that. When is an economizer required? Per the IECC 2015, it is required for cooling systems that are 54,000 BTUs and larger. Right? So that's 4.5 tons and up. And since hardly anybody has a 4.5 ton rooftop, we're essentially talking about 5 ton rooftops and larger need an economizer. 4 ton rooftops and smaller do not. By the way, the economizer rules are for both rooftops and split systems and anything else that has cooling and a fan in it. But for today's purposes, we're sticking on the rooftop discussion. There are some exceptions to that rule, if you will. For starters, if you were on the old code, if you remember the 2012, that was only 33,000 BTUs. This is 54. So they made it a little less strict. Right? Not because it was hard to do on a rooftop unit that's 3 or 4 tons, but it was hard to do it on a split. But if you are above 54,000 BTUs, there are certain scenarios that may apply to you where you do not have to do the economizer. They are not common scenarios, right? Some of these special humidified process applications, certain residential applications that happen to fall under the commercial code, systems that barely run at all, less than 20 hours a week. So like some little one-room church type thing out in the woods, right? Something like that, you might not have to do the economizer. Chilled beam type systems. Normal systems, like any packaged rooftop system, I'm probably going to have to do the economizer. For my friends in Wisconsin, you have an amendment. Your amendment is, yes, we're going to use the 54,000 BTU cutoff for all systems, right, split, whatever. However, packaged rooftop units, there is no minimum limit. Every single packaged rooftop, even if you somehow got your hands on a 1-ton rooftop unit, it would have to have an economizer on it. So in Illinois, 5 tons and up. In Wisconsin, all rooftops need to have an economizer. Some of the economizer rules, as well as some of the other rules we'll talk about today, apply to your IECC climate zone. This is the climate zone map for 2015 and most of the earlier versions as well. As you can see, northern Illinois, which would be the Chicagoland area, we're in climate zone 5. Milwaukee and southern Wisconsin, Madison, all you guys, you are in climate zone 6. Which is the blue area, and then to the right of this line over here is the moist area, A. So 5A and 6A are what most of us on this conference call are living in. In relation to an economizer, if I'm in climate zone 5A and 6A, what that essentially means is if I have a dry bulb economizer in those climate zones, I need to set the outside air changeover point at 70 degrees. So not the traditional 55, not Brian's favorite 62, 70 degrees. That means if it's a 69-degree day, you're in economizer mode. If it's a 70-degree day, you can be in compression mode. Right? Now, obviously, you're not going to cool a building with 69-degree air, so you need some compressors to help the economizer, and we'll talk about that in a second. But that would be the basic idea there. If you have an enthalpy-controlled economizer, then you need to set it for 75 instead of 70. And you get to look at the enthalpy, which is 28 BTUs per pound. That will be your top end limit. So if it's 27 BTUs per pound outside, it's an economizer day. If it's 28 or greater, it is not an economizer day. And then I also want to point out, because some people have asked about this, down here at the bottom in the footnotes, it says that you can have your set point, your 70 or 75, be plus or minus 2 degrees, and your enthalpy, 28 number, be plus or minus 2 BTUs per pound, right? So technically this 28 is really somewhere that you can choose between 26 and 30, depending on how many fine increments your controller has available to the settings, right? Same thing with the temperature. The 75 is really 73 to 77, depending on how fine of increments your control widget has available to it. So they give you a little bit of flexibility knowing that every controller can't do things in 1 degree increments. So if I was to put that on my psychrometric chart, right, I move my line from this black line at 55 over to the 70 degree number, and all of this on the left side is now an economizer day. Everything on the right is a compressor day. I do have some concerns with that, specifically these high humidity days. Over here, where I had a 90% humid day when it was 53 degrees outside, I'm not so worried about that because that was only, let's say, 55 grains of moisture over here. But now if I have a 90% humid day and it's at my threshold, say 68 degrees over here, now I'm at 95 or 100 grains of moisture. I've almost doubled the amount of moisture if I'm right here on the cusp as opposed to over here on the cusp, right? So this area right here, you probably heard me refer to it as the triangle of death. I want to avoid this area. It's too humid for me to deal with on my building, and it will increase my callbacks and problems. However, this is what the code's saying I have to do. So because of that, I am no longer recommending dry bulb economizers for small systems. I mean, for larger systems, I was always telling you guys do enthalpy, and then do the small ones, do dry bulb for cost-saving reasons. But now I'm just going to tell you to do enthalpy on everything to get rid of that triangle of death, if you will. So if I was to draw the code required lines for an enthalpy system, that 70 number moves 5 degrees to the right and becomes 75. So I have to take all these extra days right here for economizer days. However, I get to draw the enthalpy line in. Here's 28 for enthalpy. That's this line right here. And I can take everything off of that. So I trade off this little sliver for this triangle of death, right? So over here is an economizer day. This is compressor day, compressor day, compressor day down here, right? So you're probably going to want to look at enthalpy economizers instead of dry bulb if you're interested in complying with code. Now, obviously, we can't cool a building with 68, 70, 72 degree air, even though the economizer by code is going to make me take that air for free cooling. So because of that, an integrated economizer is a requirement of the code as well. What an integrated economizer means is that economizer on a cool economizer day becomes your first stage of cooling, and then the mechanical compressors can be engaged after that as needed. In order to do that, you need a two-stage thermostat. Even if you only have one stage of compression, you still have to buy, install, and wire a two-stage thermostat, Y1 and Y2, because that's how the economizer controller is going to know that you're not getting things done in the space with just the economizer by itself. So Y1 on the thermostat calls for cooling. The economizer checks to see if it's cool enough or dry enough or both outside. If it is, it goes into economizer mode and modulates the mixed air damper to maintain 53 degree discharge air, or 55, whatever you set it for. Then if it's still not getting cool enough in the space, the thermostat will recognize that and it'll energize Y2. Y2 will go up to the economizer controller. The economizer will open his damper fully, if it wasn't already open fully at that point, and then say, dude, what the hell do you want me to do? That's the best I can do. I'm going to have to turn on your compressor. And then Y2 will actually get pushed over to the compressor number 1 and engage him. That's what an integrated economizer would do. And that is a requirement of the code. There are some other rules that do kick in when you have an integrated economizer. For one, you can no longer have hot gas bypass. Well, you can have hot gas bypass on the smallest stage, the lowest stage of mechanical cooling, but you cannot put it on the stage 2 compressor or any of the other compressors, right? And there's also some other requirements down here, number 2 and number 3. I'm going to address those later because I don't feel they really belong in this section as far as discussing them. So I'm going to discuss those in a few minutes. If I look at the entire scenario all at once, right, with the enthalpy line and the temperature line on there, this over here becomes my compressor days. Over here is my economizer day. And somewhere between 55 and 75 in this scenario, I'll have integrated economizer, meaning my damper will be opening to provide free cooling, but it might engage the compressor as needed. Right, if I'm below 55, I shouldn't need the compressor at all. If I'm above 75, I definitely will not use the economizer, but in this middle area, I could be using both together. If I add one more column to that same example, right, we had the base entry-level unit that you could possibly find on a shelf somewhere, a code-compliant unit as far as EER and IEER go, and now I'm going to take that code-compliant unit and I'm going to add a code-compliant economizer to that unit and calculate all three of these guys and their energy usage. When I do that, like we saw before, I was only saving 1% to go to the code EER unit, but then once I add the economizer, I save an additional 6% on top of the 1%. So the economizer is pretty impactful for energy savings and a much better way to save energy than just putting a more efficient refrigeration plant in the unit. Other things going on with outdoor air economizers we should be aware of. If I'm going to suck a bunch of free air in for cooling reasons, I also need to have a way to get the air back out of the building, so you need some sort of pressure relief. That could be a barometric relief on a system that's small, and by small I mean not a lot of resistive return duct on it. If it gets bigger and hence more resistive, then I'm going to want to put a power exhaust in to draw that air back out of the building instead of just waiting for it to get there on its own. Right? So I got to have some way to deal with that. I have to have an occupancy interlock. An economizer, as you probably know, doubles as my ventilation system and my free cooling economizer. My ventilation requirements for the building, whether I'm following IMC or ASHRAE 62 or whatever my local municipality follows, those requirements, I'm only required to bring the ventilation air in when the building is occupied. When the building is unoccupied, those codes don't make me bring vent air in. Additionally, IECC, the energy code, tells me that I can't bring the ventilation air in when the building's unoccupied. I need to shut the ventilation damper. In order to do that, something has to tell the economizer controller that the building is unoccupied. That something, well, it could be a DDC system, right? But if you don't have that, that something is going to end up being your thermostat. So your thermostat is probably the only thing that knows the occupancy schedule of the building. So the thermostat needs to have an extra output on it that wires up to the economizer controller and tells that damper to shut off when the building is unoccupied and not bring the ventilation air in. Otherwise, every time you turn the fan on the rooftop unit, the economizer damper is going to open in the middle of the night on a heat call on a minus 10 degree day for no reason at all. So that is required. You need that interlock, and most of people have not been doing that. Additionally, the dampers themselves, when they are shut, they need to be really shut tight. So all night long, when we're not using those dampers for ventilation or anything else, we don't want cold air leaking in or hot, humid air leaking in the summer. So we need to have a tight seal off. The energy code requires all shut-off dampers, which would include packaged rooftop unit economizers, to be low leak dampers, which means that they can only leak a maximum of 4 CFM per square foot when tested at 1 inch of pressure. They get a little AMCA 500 stamp on them to indicate that they do in fact comply with that. So all economizer dampers for all size units, even if you put an economizer in on a 2-ton rooftop unit, even though the economizer wasn't code required, all the dampers have to have this, right? So what does that, physically look like in the field? That means your damper, when you buy a low leak damper from your damper supplier, Micrometal, Carrier, whoever it is, you're going to have edge seals and end seals on the blades. That kind of was obvious. And then the gears, which historically have been internal to the airstream, will now be moved out of the airstream. And it'll look like the picture on the right there. Previously, with the gears in the airstream, they couldn't be perfectly airtight because they're gears, and gears have to move, and things that move struggle to be airtight. So therefore, the gears have been moved to the outside of the assembly. Not outside the rooftop, just outside the damper assembly, outside the airstream, if you will. So that's a good way to visually check and see if someone put the right economizer dampers in to comply with code or not. Are the gears in or out of the airstream? You guys have probably seen this chart before as well. It is a study from, 10, 12 years ago, 500 rooftops at 180 buildings. This is the most common problems that were found on these existing buildings, right? Half the time they had the wrong charge. Half the time they didn't have the correct airflow, too much or too little. Half the time the thermostats were not programmed, configured, or wired correctly, right? And 64% of the time the economizers were not functioning correctly. That means the economizer was screwed shut, or the economizer damper was propped open, or the economizer motor was turning, but it wasn't connected to the shaft, it was just laying on the ground, or the linkage arms on the economizer blades were broken, or the set points on the economizer were all jacked up. Something was not allowing it to work correctly. Because that is a pretty high number, more than half of the economizers in the field are not working correctly. And by the way, there's a similar study from Honeywell that shows 70% of them in the field are not working correctly. Because of that, the code folks have jumped on that, and they've made this a new requirement. So you'll see in the 2015 code and later versions, you're required to have fault detection and diagnostics, FDD, on your economizers for DX systems. What does that mean? This is all the language of what that entails. I'm not going to read it to you, but basically your economizer controller needs to babysit itself and make sure that its temperature sensors don't get out of whack, make sure it doesn't bring in too much air, too little air, make sure it's not running the economizer when the heat's on, all these sorts of things. So it's got to babysit itself to do that. The Honeywell Jade controller pictured in the corner there does that. I believe the Honeywell Zip controller does it. Most of the DDC guys can write their code to make it do that, right? So it's not too hard to get this if you ask for it. What makes it a little bit hard from an application and field standpoint is that item number 6, the unit shall be capable of reporting faults to a fault management application accessible by day-to-day operating service personnel. That means that economizer controller needs to send its alarms to the building automation system and pop the alarm up on the building operator's screen, or email him, or text her, or whatever it's going to be. You do not have a DDC system, hence you don't have a fault management application system. Then your choice becomes enunciate locally on zone thermostats. That means your thermostat on the wall needs to tell you that there's some kind of fault with your equipment upstairs. It could say economizer fault, it could say unit fault, it could say alarm, alert, right? It's basically a check engine light. I don't know what's wrong with it, I just know something's wrong. What you cannot do, and some people have tried this, is say, well, the screen on the economizer controller says the alarm, so that's good enough. That is not good enough because it is not accessible to day-to-day personnel. There's not someone sticking their head in that rooftop cabinet every single day. The state of Illinois has made an interpretation that that does not count, and you must enunciate it down at the zone thermostat. I don't think Wisconsin's made such an interpretation, but many states have, so it's kind of implied at this point that you need to put it on the stat. Unrelated to the energy code, I just want to point this out while we're on economizers because I still keep getting this question. The city of Chicago proper used to require the outside air intake of a packaged rooftop unit to have 15 feet of duct added to it to keep it away from all sources of exhaust systems. That requirement is still in effect. However, there is a new exception to that. By new, I mean 2 years ago. A new exception to that, it does not have to be 15 feet away from itself. So it does not have to be 15 feet away from the power exhaust or the barometric or even from the inducer exhaust. They decided that a packaged rooftop unit, someone has designed and engineered it to not have those airflow paths interfere, so you no longer need that 15-foot duct extension. You still got to be 15 feet away from some random bath fan or whatever, or kitchen fan, but not 15 feet away from itself. All right, controls as related to rooftop units. Thermostats are required to be 7-day programmable. You cannot use non-programmable. You cannot use a 5+2. In fact, if you buy a commercially listed thermostat, the only one you will ever see is going to be a 7-day. There is no 5+2 commercial thermostat that I've ever seen on the market. Those are residential stats that somebody's misapplying. So 7-day programmable. Got to have at least a deadband of 5 degrees between the heating and cooling set point. That means if you decide you're going to heat the building up to 70 degrees, you are not allowed to cool it below 75. You must maintain a 5-degree deadband between the heating and cooling set point at all times. You can't overlap the set points, which is kind of redundant because if you can't get them within 5 of each other, how the heck are you going to overlap them? You got to have a way for the occupants to override them. You can't put a stat in the room, put a lockbox on it, and give nobody any options. You got to give them some way to override it, either with a motion sensor or a timed override button, where they can get a few hours of cooling and heating without having to jerry rig and stick paper clips in a lockbox. You know you've done that. The thermostat has to have, or thermostat or the controller, if you got a DDC controller, same thing. The thermostat or the controller has to have optimal start routine. There's numerous different names for that out in the market. But basically, the system starts calculating when it needs to begin heating and cooling function in order to have it at set point at the time you say it's going to go occupied. So if you say it's going to go occupied at 8 o'clock, you would set it for 8 o'clock. Whereas a regular stat, you would set it for 6 or 7 in the morning. This one you would still set for 8 when walking in the door, and the stat would calculate, oh, I need to start at 7:23 today, so it's perfect temperature when Ryan walks in the door. You got to have the shut-off damper for outside air ventilation like I talked about. So the thermostat needs an output to tell the ventilation damper or the economizer damper, same thing, when to be open or closed for occupancy. And then the thermostat needs an input on it to accept FEV alert. At the time that this originally came up, Illinois had made a FAQ on their website that listed the 3 thermostats that complied with this. There's more than 3 now. There's a whole bunch of them. It's still not a big list. It's still like, I don't know, 8 or 9 on there, and most of them are just similar versions of each other. There's a pretty short list of stats that'll do it. The one we use at TEC quite a bit is the Ventstar T4900. There's also 3 or 4 Honeywell models that'll do it. So there's options out there now. Sometimes demand control ventilation with CO2 sensors might be required. It is not always required, only sometimes. I'll explain when it's required. But for those of you that don't know what it is, let's just briefly talk about what demand control ventilation actually does. So this is showing you an actual building. And this is from the, let me get my little pointer there. This is going from midnight to midnight. And it's going from the ventilation damper being closed to wide open. Now, wide open is not the economizer going 100%. It's 100% of the ventilation air, which may only be 15, 20, 25% of the economizer itself, but full ventilation, right? So at 7 o'clock in the morning, the building, or what is it, 8 o'clock, whatever that says, 8 o'clock in the morning, the building goes occupied. The ventilation damper would go to its occupied position. It would stay there all day long. And then at 6 o'clock at night, when the building closes, it would go back off, right? That'd be a normal system. When you put CO2 sensors in there, the CO2 sensors detect how many people are breathing in the space. And the less people in there breathing, the less occupants there are, hence the less code-required ventilation I need. So in that case, instead of going wide open, it only opens as far as it needs to for the amount of people that show up, right? So that's like the purple lines here. People come into work late, surprise, surprise. They leave for lunch early, no surprise also. Some of them stay for lunch, some of them leave. Most of them make it back, and then people start cutting out early to go to the dentist or golfing or whatever the heck they're going to do. So I hardly ever get the full green occupied pattern. I get this, in an office building anyway, I get this 2-hump, profile type thing. Restaurants, similar thing. They get a 3-hump profile, right? Most of these building types have pretty predictable usage on them. There's quite a bit of savings that can be had by doing demand control ventilation. We have an entire webinar, our webinar on that. If you want to check it out on our website, you can. But I just want to give you a little background on that. So when is it required by energy code? For the 2015 code, if you have a space that has a density of 25 people per 1,000 square foot or greater, you're likely going to have to do it, right? Really small spaces don't, right? Smaller than 500 square feet, but that's really small. It's like one dude's office, right? But if it's bigger than that and it has more than 25 people per 1,000 square foot, so think movie theater, auditorium, gymnasium, those kind of things, you're probably going to have to do it. There's some exceptions, like if you have an ERV, you don't have to do it because an ERV and CO2 both dip into the outdoor air energy savings, right? So they kind of overlap a little bit, so you don't have to do it in those cases. If you got small systems that have less than 1,200 CFM of ventilation air to begin with, right, there's some exceptions to that. But for the most part, you're probably going to have to do it for densely occupied spaces. So not every rooftop unit, but certainly every rooftop that's on a movie theater or a place like that, right? And I'm stressing not every rooftop unit, because that's probably going to be a quiz question later. Wisconsin has amendments. They rolled that 25 number back to the 2009 code number, which was 40. So they don't have quite as strict a requirement as the other states that are following 2015, like Illinois has. If I add one more column to that same example, I'm going to add, in this case, code compliant unit with an economizer and demand ventilation, right? Now this is on an office building example, so it won't be as robust as it would be on a movie theater, but still should be decent. I'm getting 1% for the unit's efficiency, an extra 6% for the economizer, and another 6% for the demand control ventilation sensor in this case. Right? It's a pretty cheap sensor, relatively speaking, compared to the cost of a unit, so it should be pretty beneficial for a lot of applications. All right. You probably have seen this chart as well. It comes from a 2013 Pacific Northwest National Lab study for advanced rooftop control systems. This particular chart is showing you how the fan is used on real projects. So the red bars on the bottom, that's when the fan is running for heating mode. The blue bars on top is the fan running for cooling mode. green is for economizer, purple is for integrated economizer, meaning the economizer and compressor together, and then baby blue is when the fan is running for none of those reasons. None of those reasons would be ventilation for code required ventilation air. So as you can see, baby blue, ventilation mode, is pretty much the dominant factor. He is the reason that the fan is running so frequently. So making more efficient heating and cooling systems via code requirement only gets you so much. At some point, we got to pick on the ventilation fan to get more and more efficient here. So that's what the codes are doing now. So because of that, in the 2015 code, there is a section for required fan speed control. Now, unfortunately, that section, C403.4.1.1, that's a mouthful, fan airflow control, that was supposed to be its own section in the code, but it got stuck under 403.4, which only by definition applies to hydronic systems and multiple zone systems. It does not apply to regular everyday single zone systems. This gets fixed in the 2018 IECC. This splits over to the left here and becomes its own code number, its own paragraph number, if you will, and applies to all rooftops. But right now, that's not the case for Illinois and Wisconsin because we're on the old code, 2015. So for right now, this only applies if you have hydronic coils, meaning chilled water, hot water in your rooftop or other air handler, or you have multiple zone systems, which means zone dampers, VAV, VVT, things like that. If you have those zone systems on there, then if your rooftop unit, DX cooling, is greater than 65,000 BTUs of cooling, so more than 5 tons, if more than 5 tons, you need at a minimum a 2-speed fan on there. You can push it and go farther and have a fully variable speed fan if you want, a VAV style fan, right? But at a minimum, you need a 2-speed fan, often referred to as staged air volume, SAV, right? So as soon as you have zoning, you need more than 1 fan speed, unless it's a really small system, 5 tons and under. The way that typically works for most rooftop units is that if you're in full cooling mode, 2 stages of cooling, yep, you're at full fan speed. If you're in heating mode, you're at full fan speed. If you're only in stage 1 of cooling, then you drop down to 2/3. Or if you're in vent only mode, which is a lot of the time, you drop down to 2/3 fan speed. If I take a code compliant unit, IECC 2015 compliant unit with a code required economizer, and I take that exact same unit, same model, same coils, same compressor, same everything, and I just simply put a 2-speed fan in there and make no other changes, and I hit calculate on my little software tool here, it's a 30% savings, right? So going to a more efficient rooftop was 1%. Going from a more efficient rooftop with a staged air volume fan is 30% savings. It's a pretty big number. So you can see how impactful saving fan energy is and why that's getting picked on in the energy codes now. So you're going to see more and more of that. Right now at TEC, our default stock unit is a staged air volume unit. There's certain sizes we don't do that, but for the most part, 90% of what we're quoting you is going to have a 2-speed fan on it for the past 2 years. Now, a 2-speed fan, we don't typically use a 2-speed motor. We typically use a VFD on a single-speed fan because a VFD, the costs have gone down so much, it's actually less expensive to buy a VFD, program it for 2 speeds, than it is to actually buy a 2-speed motor with double the windings in it. Additionally, on zoning systems, remember I said we're going to come back to the integrated economizer control? This is that same language we had there, but now we're going to jump over to where it says number 2 on there. Right? So if I have a DX system that is 75,000 BTUs of cooling or more, I am required to have 2-stage cooling for both zone systems and non-zone systems, all systems, which would include rooftops, obviously. So as soon as you get over 6 tons, you better have 2 compressors in there, or 1 compressor with 2 stages, or 1 compressor with a VFD or something like that. Right? Additionally, and that's pretty straightforward, nobody gets that. Additionally, number 3 has been a topic of discussion at the state level, as well as with designers. Other DX units, including those that control space temperature by modulating airflow to the space. Who's modulating airflow to the space to control space temperature? A VAV system or a VVT system or any zone damper system. The thermostat says I want more or less cooling, and it throttles back the airflow to that space to get the more or less cooling. So as soon as you put zone dampers, VAV, VVT, I don't care if it's a little tiny Honeywell 3-zone panel, whatever it is, as soon as you put zone dampers on there, then number 3 kicks in. That puts you down at the table at the bottom. That means if you got 65,000 to 240,000, so if you had 6 tons to 20 tons, you need 3 stages of cooling. If you have more than 20 tons, you need 4 stages of cooling, right? And don't forget, we also have that limitation on hot gas bypass. Hot gas bypass does not count as a stage. You can have it on the smallest of your 3 stages here if you want to, but you still need 3 stages in addition to the hot gas bypass, right? So that makes things a little bit different. There are additional limits on hot gas bypass, right? So if you don't know what hot gas bypass is, just kind of the quickie tutorial here, right? Here's my evaporator, here's my condenser. They're kind of a yin and yang to each other, right? One absorbs heat, one rejects heat. And I have my compressor, which raises the pressure and temperature. Then I have my TXV, which meters it back into the evaporator. They're kind of a yin and yang of each other. What happens with hot gas bypass is instead of the compressed refrigerant going to the condenser, where it can reject the heat, some portion of that bypasses the condenser and gets shoved back into the evaporator. So I'm literally going to take this hot gas and shove it into the evaporator coil, which falsely loads the evaporator coil and hence makes it run longer to actually meet the set point demand, right? So it is not an energy saving thing at all. It's a massive energy penalty. It solves my problem of short cycling my unit, which is great, but I have to do it at quite a high energy price. So we really want to minimize the time that gets into effect. So we had the hot gas bypass limit we just talked about. If you have an economizer, that hot gas bypass limit comes into play. Units with economizer can only put hot gas bypass on the lowest stage of mechanical cooling. Additionally, and unrelated to economizers, in that hydronic and multi-zone section, right? So if you have a zone damper system again, you have another hot gas bypass limitation. For starters, you can't use it. As soon as you have zoning, you can't have hot gas bypass. That's what the language would say, right? Unless you're going to put in multiple stages of compression or unloaders, right? So we already saw that once we're above 6 tons, we have to have multiple stages of compression, right? So really, we're only talking about stuff that's 5 tons and under. If it's 5 tons and under, single stage unit, you cannot put hot gas bypass on there. It's only like weird scenario. Although usually systems that small don't have additional zoning, so it's a non-issue. If you do have bigger units and you choose to put the hot gas bypass on there, you can only bypass up to 50% on a 20-ton system and a maximum of 25% on a larger 20-ton system. This language has been in here for a while, and it's kind of dumb now that we have that other limit that we just talked about right here. Right? They're kind of redundant and overlapping with each other. But nonetheless, it's 2 separate rules, so I wanted to point them out. They could theoretically kick in a different scenario. Try not to use too much hot gas bypass. From a carrier perspective, to put a little plug in there, the 4850 LC does a fantastic job of complying with all of these things that we're talking about. 3 stages of cooling, staged air volume fans, VAV fans, super high IEER, right? All the kind of things that we're talking about that you need to pretty much get to. All right, quiz question number 3. Which of the following are required on a typical 10-ton DX RTU installation? I've used this question a couple weeks ago, so you guys should be able to get this, I would hope, but hopefully so. Which of the following are required? A, 12.6 IEER. B, an integrated economizer. C, fault detection and diagnostics. D, 2 stages of cooling. E, all of the above. Which of these things are you required to do on a typical 10-ton unit? Don't see any new questions typed in. I'm wondering if that's because a lot of you guys were on some of the previous webinars and hence there's quite a bit of overlap, or if it's just because I'm awesome and explain everything perfectly. I'm going to go with the latter. All right, I'm going to close the quiz question in 5, 4, 3, 2, 1. And the correct answer is, in fact, E, all of the above. And you guys all got it correct. I'm so proud of you. All right, quiz question number 4. If a zoning system is applied to that same previous 10-ton rooftop example, which of the following is also required as a minimum? So it's the same 10-ton rooftop we just talked about, and now it has zoning on it. What else do I have to absolutely do as a minimum? Choices are A, 3 stages of cooling, B, staged air volume or true VAV, C, demand ventilation, D, 3 stages of cooling and staged air volume, or E, 3 stages of cooling and demand ventilation. We're getting there. Good majority of you are getting it right, although there's a few errors on here. All right, I'm going to close it in 5, 4, 3, 2, 1. All right, well, 50% of you actually ended up getting it right, A and B. 3 stages of cooling is required on a zoning system. That's 10 tons. And staged air volume fans, or VAV, are required. So A and B are both required, so the correct answer is D. Only 50% of you guys got that. Some of you guys were thinking the 3 stages of cooling wasn't kicking in there. Just to recap, I'm going to go back to it just to show you so that way. Right? So if you're looking at this guy here, number 3, units that control space temperature by modulating airflow, which we said was a zoning system. The zoning system, I have to do this table down here. 10 tons falls in this right here, which is 3 stages of cooling. All right. I just showed you guys a screen. I went to a screen and didn't show you the screen. So that was very unfortunate for you. I was talking about this here. Number 3, control space temperature by modulating airflow, which we said was zoning. State of Illinois has interpreted that to include zoning. That kicks in the bottom table here. So 3 stages of cooling is required. All right, a few more rooftop-related requirements here to wrap us up. Energy recovery ventilators. I'm not going to explain how those work. We have a whole entire 1-hour webinar on those. Plus, we have some videos on our YouTube channel that physically show you the pieces and how everything works. So you guys can look at that if you want to know how an ERV works. But when is an ERV required? Well, if you're going to use an ERV, right, if your code required to provide an ERV, it has to be 50% total enthalpy recovery. That means you cannot get a sensible only ERV, an HRV. That would not comply with code. You got to do 50% of the total. So if you're only doing heat and cooling and you're not doing humidity, you're not going to get 50%. So HRVs are automatically out for code compliance reasons. ERVs, enthalpy recovery ventilators, are in. So once you go to that category, you can either use a ERV enthalpy wheel or you can use a enthalpy core. You cannot use the fixed plate metal core. You cannot use a runaround pipe. You cannot use a heat pipe. You cannot use any of those kind of things. You're kind of limited there. The good news is, as far as rooftops are concerned, almost all the ERVs are either wheel-based ERVs or they are cores anyway. There are some exceptions here, as you can see, 11 of them listed out. Most of them do not come up in your everyday projects. The one that will come up at reasonable frequency is number 8, where the largest source of exhaust air at a single location is less than 70% of the total design outdoor airflow rate. So essentially, if you have 2 equally sized exhaust fans for the building, you might not have to do an ERV. So think of like a makeup air unit on a condo tower or something like that. You might get out of it. But if you're not in that scenario, then when do you have to do an ERV? New code splits it into 2 tables, 8,000 hours per year and less, or 8,000 hours per year and more. There's 8,760 hours in the year. So essentially, the top table is telling you you're not running this all year long. This is what you'd have to do then. So for our climate zones, 5A and 6A, depending on the fraction of outside air, right? If it's 70% outside air and 1,000 CFM of supply air, I need an ERV. If it's above 80% outside air, like a DOAS system, I always need an ERV, right? Automatic. Right, and then the table tiers down below that. Then when you get to the more than 8,000 hours a year type of thing, so basically running almost year round, all systems that have 10% outside air or more would have to have an ERV. So a lot of hospitals fall into this category. What else would fall in there? I guess technically like a 24/7 Walgreens might fall into this category, something like that. If we look at a little comparison there, I got a code-compliant rooftop unit with a code-compliant economizer, and now I add an ERV to that rooftop unit. This is the same 10-ton example we had before. In this case, it's going to save me an additional 7%. That's not a high outside air requirement project. If it was, like a nursing home or something like that, or a school, then that number would be much better. But that's the same 10-ton office example we've used in all the other slides, so it's a mediocre ERV payback. I also want to point out that I could take all of these things we talked about, right, and I could add them all up. And if you look at all my little software calcs we did throughout the presentation, you'd be like, damn, Ryan said we can save 105% of the energy. No, it doesn't work like that. These things overlap with each other, right? So if I put an economizer in, that affects my DCV savings. And if I have a staged air volume, it affects my economizer savings, and so on down the line. So if I look at all those things and I did them all together, right? If I just go from the worst column on the left, 15-year-old, unit that wasn't super efficient, to all the way on the far right, which is a fully loaded Carrier 48LC with 3 stages of cooling, 2-speed fan, DCV, ERV, economizer, everything loaded up in there, and compared them against each other, it would save me 62% of energy. Right? Which is a pretty good chunk. I'm not going to get all those features on one unit, or if that's even necessary, but if you did, it would be a pretty big savings. You guys have probably heard me complain about duct leakage as well. We have a whole entire recorded webinar on our website related to duct leakage, so I'm not going to beat on that repeatedly. Just know that ducts leak. Ducts leak pretty bad. There are tons of statistics from ASHRAE and others that support how bad they leak. The new ASHRAE Green Building Standard has some requirements for duct leakage testing on there now. But for today, we are in the IECC. So what are the requirements related to duct sealing, duct insulation, and duct leakage? First of all, insulation. The insulation needs to be an R6 level if it's in an unconditioned space. Right? So I know what that would be exactly. You have to read the definition, but it could probably be like if you had a little bank job and the duct was running through like some kind of attic type area, something like that. Right? If you're going to run the ductwork outside, like true outside, you need R12 insulation. Right? This is what's required for energy code. You may need insulation for other reasons, like for mechanical code or for duct sweating reasons, right? Just for good engineering practice. But as far as energy code goes, if it's in the building, you don't need anything. If it's in an unconditioned or semi-conditioned space, you need R6. If it's outside, you need R12. All the ducts have to be sealed on all projects. Then after that, ducts get classified into 3 buckets. Low pressure, 2 inches and less, design static. Medium, 2 to 3 inches. And high, over 3 inches. And it gives you the specs on how you have to seal those ducts on there. The thing I want to point out is once you get to 3 inches and higher, not only do you have to seal the duct, but then you also must leak test the duct and pressure test it. So either you have to do that, or you have to look at your design really hard and be like, do I really need 3 inches of static? Can I get it done with 2.6 or something like that? And reevaluate that decision. Otherwise, you're going to have to seal the ducts much better in order to pass one of these leakage tests because they're pretty stringent. So that's part of your rooftop project as well. This is not part of your rooftop project because it can't be, but people will try to make it be. So that's why I want to talk about this. In the IECC 2015, this is our last thing. We'll wrap up here, get our last quiz question for you. There's a thing called package C406. It says, good job. You did everything we told you to do in the code book. But now you must pick one of these 6 extra things and do one of them. You're like, what the hell, man? I just did everything. Nope, one more thing. And they give you these 6 choices and you can pick one. Most projects go with number 2, reduce the lighting density. And it doesn't affect you other than your load calc, and you don't pay attention to it. Sometimes the architect will come to you and say, hey, we're going to do number 1. I need you to make everything comply with this 406.2. Okay, no problem. And then you go read it, and you realize basically all the HVAC has to get 10% more efficient than the code book. All right, no problem. Easy enough to do. Yeah, easy enough if you have a boiler and a chiller. If you got a packaged rooftop unit, I can get you 10% more efficient on the DX. How am I going to get you 10% more on the gas heating section? Right? 80%, 10% more efficient would be 88%. Not too many people make an 88% condensing rooftop unit. That's not a thing. So if you're doing a rooftop project and your architect designer wants you to go down path number 1 here, you need to either push back and say we can't do it, or you need to say we're going to do it for you, but now it's going to be a chiller job and not a DX job. At least not a DX rooftop job. right? It could be DX air handler with a boiler. That could be, you could do it that way, I guess. So I point that out on there. In Wisconsin, you do not have to do C406 at all. Wisconsin made an amendment to eliminate that. So only in Illinois and other IECC states would you have. All right, our final quiz question. True or false? All rooftop supply and return duct must be sealed. For you guys that gotta go after you answer this question, you guys could check out if you want to. I got 2 more slides I'm going to show you about rooftop efficiency, what's being required by other non-IECC things. But there's no more quiz questions after this, so if you got to check out, I get it. But if you guys can stick around for 4 or 5 more minutes, I'll give you a couple other very interesting things to look at and consider. All right, I'm going to close this quiz in 5, 4, 3, 2, 1. All right, 90% of you got it correct. It is true. All the supply and return ducts must be sealed on rooftops or any other duct systems for that matter. So you definitely have to do that. All right, last thing I'll share with you guys that are hanging out here with me. We've been talking about the IECC and what's required there. As you know, the energy codes are policed at the local jurisdiction, either state, city, or sometimes county level, right? They have no bearing on the manufacturer and what they do. They have no bearing on TEC, the distributor, what we do. We can sell you outdated stuff from years ago that has no chance of complying. We could sell it to you if we wanted to. You just can't legally install it, right? That's kind of how the weird thing is. The codes are policed at permit time, and then they're policed at inspection time. And there's no requirements for us, a selling entity, to comply with that. However, there are other requirements that do affect us meaning TEC, Carrier, Bryant, and so on. So that's the Department of Energy. They set rules for minimum efficiencies of various things as well, and they do have rules for minimum rooftop efficiency. And these are the rules that went into effect as of January 1st of this year, nationwide. No manufacturer can make anything that's less efficient than this. This is the legal minimum efficiency thing they cannot possibly build. There are no requirements on there for EER, full load. That's been totally dropped. The federal government said full load doesn't matter because there's no run hours there, or almost no run hours. There's no requirements presently for fan speed control, cooling stages, economizers, anything else. It's just an IEER requirement, right? So that's the requirements of what it is, right? So for 10-ton unit, you got to be 12.7 IEER. If we look at some of these levels compared to each other, I got 3 columns on here, and I picked 3 sizes, 5, 10, and 15 tons. There's the Energy Star requirement, which theoretically should be the most efficient thing out in the marketplace. And at the time that standard was written, it was, but the codes have surpassed it, and the DOE rules have surpassed it. So the Energy Star is absolutely worthless. If someone says they need an Energy Star rooftop, say no problem, because you couldn't buy anything worse than that anyway. If I look at the 2015 code as compared to the 2018 code, there's going to be no changes. So in Illinois, when we go live with the 2018 IECC next March, it will not affect your rooftop efficiency. It'll affect other stuff with the rooftop, but not the efficiency of the EER and IER. But if I look at the code, IECC, compared to the DOE column, Department of Energy column, there are some slight differences. For starters, it doesn't apply to residential side equipment. Residential, once again, means 5 tons and under, 65,000 BTUs. There's no minimum there. Look at the 10-ton unit, there's no EER requirement, but I got to be 12.7 IEER. It's like 1/10 off from the code number. I don't know why they couldn't make them the same and make our lives easier, right? But you'll see that happening. So if we still have something in stock, you could get this for your code compliant project, but once the stock is out, you would have to get this guy over here. Right? So just pointing that out as a change that's coming down the pipe, or actually came down the pipe as far as manufacturing goes, and now it's starting to affect inventory. Other resources, if you're interested, this is the 3rd week in a row we've done an IECC related webinar, because once again, it's a new change in Wisconsin, so lots of people were asking, and we figured if we're going to do Wisconsin, we might as well do Illinois with it and just help all of our customers at once. If you need help with any of those webinars and watching them online, tecmungo.com/training. You can sign up for training classes there. You can watch our YouTube video series there, which is 10-minute type videos, or you can watch recorded webinars like this one we're looking at today. I'm going to look and see if there's any other questions you guys typed in, and then I'm going to try to answer those for you guys here. So Jeff types in, is it possible to modify an existing RTU to achieve SAV, staged air volume? It is absolutely possible to do that, Jeff. You can do that, and not only can you do it, but ComEd Electric in Illinois and Focus on Energy up in Wisconsin will pay you incentives, rebates to do that. So the fan technically would have to be inverter duty rated motor, which most of them are at this point. If it wasn't, you probably could still put a VFD on it, and it probably would still be fine. It just might not have enough insulation on the windings to keep the life of it really long. We can do a whole different discussion on that. There are times when that makes sense and times when it doesn't. If you got a 15-year-old rooftop that's only going to be up there for another 2 to 5 years, I would not invest any money in modifying it. But if you got a rooftop you put up there 3, 4, 5 years ago, it might make some sense to do that. But yeah, you can absolutely do that. There are manufacturers that make kits to do staged air volume. Typically, it's called ARC, Advanced Rooftop Control. It includes a controller, economizer, demand control ventilation sensors, and staged air volume VFD fan. There's three manufacturers that make kits for that. Also, I've been making my own kits with off-the-shelf Honeywell parts, stuff that we've stocked for decades here. I got a wiring diagram and a parts list, so if anybody wants that, hit me up and send me an email. I'll be happy to forward that to you. You can build your own kit if you like. And then, of course, you can do it with DDC controls, too. One more question on here. Jeff also asks, if the system only requires barometric relief and therefore no exhaust, 75% exhaust at one location, is an ERV still required? All right, that's an excellent question, Jeff. Let me scroll back to that language so we can talk about it. So he's talking about here, right? So an ERV is required based on this table. If you're in the bucket of needing an ERV, there are these 11 exceptions that would let you not provide an ERV. He's talking about number 8. Right? So in this case, if your only exhaust, Jeff, if you only have one rooftop total for the whole project, and it has barometric relief, and it's less than 75%, then you would have to do the ERV. If you were in this bucket with these tables right here, right? Now, the chance of you only having one rooftop on the job is kind of low. The chance of you not having any other exhaust sources kind of low also. You probably got bath and toilet exhaust and maybe other stuff too. But yeah, that could kick in here for sure. So the largest source of exhaust air at a single location, in this case, would be your rooftop unit. Yeah, you might have to do it. Hopefully that makes sense. Other questions from anybody? Most of you logged off. We're down to the last 30 people that are still hanging out with me here. So you guys that did the quiz questions and answered them correctly for PDH hours, as you probably learned from other webinars, we grade all those manually, unfortunately. So it takes about a week to get through them because there's usually 100 plus people on these webinars to get through all of them and type up all the certificates and send them out. So you'll get them this time next week. Right? And if you didn't for some reason, that either means you didn't pass or it means we're slow. But it should take about a week or so. All right. Thank you guys for your time. And if you need anything in the future, give us a holler. And you can watch this recorded webinar in about 2 hours in case you're really bored and want to watch it again. All right. Thank you.